Welcome to the next session of greedy algorithms. So in the last session we looked into this problem of encoding a file in an optimal manner. Okay, and if you just recall, you had a text file. For every character you are counting how many times it is appearing in the file, so you get the frequency of the character, and you want to encode this file using something unique binary string which is called code words. And then we saw that variable length encoding always gives a better mostly gives a better than a fixed length code compression. And the idea is that you give frequent characters short code words and infrequent characters long code words. And we just looked into that example where we had 6 characters A, B, C, D, E, F, where A appeared for 45,000 times, B appeared for 13,000 times, and so on. So total number of characters in the file is 100,000. If we use fixed length encoding, we will end up spending 300,000 bits. Whereas if we use variable length encoding as given in the last row, you will spend only 2,24,000 bits. So there will be a 20% improvement. And then we looked into that then we looked into what is called a prefix code, and we said that how do we represent a prefix code using a full binary tree. Okay, and then we looked into the Huffman coding algorithm, which allows you to make an optimal prefix code. Okay, fine. So we want to first prove today that Huffman coding algorithm works. Okay, it's a greedy algorithm. So what is the optimization problem? The optimization problem is to come up with an optimal prefix code. Okay, and in order to do that, we saw that corresponding to every prefix code there is a full binary tree. Okay, so corresponding to the optimal prefix code also there is a full binary tree. And last time we saw that how we can build this full binary tree using Huffman code algorithm, which was using a greedy choice. Okay, the greedy choice was using the least frequent character and the second least frequent character, taking those two, making the least frequent character as the left child, second least frequent character as the right child, and creating a parent node for it. The frequency of the parent node was the sum of the frequencies of its children, and then this particular new character was inserted into a priority queue, where this priority queue was based on the frequency of the characters. Okay, and we kept on doing this till our tree was built. Okay, so here we will prove that it's going to work. So recall, there are two ingredients you always need to look into: the greedy choice property and the optimal substructure property. So first we will prove the greedy choice property. So let's say that C be an alphabet in which each character small c belongs to C has frequency C dot frequency. Okay, so these are just notations. We are saying that, okay, I'm picking up a character from my alphabet C with frequency this much. Okay, that's the notation. Let's say X and Y be two characters in C having the lowest frequencies. So X is the least frequent one, Y is the second least frequent one. Then the claim is that then there exists an optimal prefix code for C in which the code words for X and Y have the same length and differ only in the last bit. That means it is saying that there exists an optimal, so it's question of an existence, that there exists an optimal prefix code for C in which the code word for X and Y have the same length. That means from the root the length is same. Okay, the depth is same. Okay, that means they must be siblings. Okay, fine. They might not be though. Okay, So what it is saying is there must exist an optimal prefix code for C in which the code words for X and Y have the same length and differ only in the last bit. So remember the way we are doing it, always the left child is getting this 0 and the right child is getting 1, the code 0, the bit 0, and the right child is getting bit 1. So it is saying that they will be of the same length, so X will have the same length as Y, only thing they will differ in this last bit. Okay, so if this guy is 0, then this is 1, and vice versa. If that is 1, this is 0. Rest everything is same. That means, and there will be such a tree or such an optimal prefix tree. That means in an optimal prefix tree always I will have, so not in any, there exists some optimal prefix tree in which X is the least frequent character, Y is the second least frequent character, and I got a node such that this is Z, such that this X is left child and Y is right child. Okay, because if that is the case, then you will get this substructure, right? You will get this encoding of X where the depth of X is same as depth of Y and they will differ in their last bit. Okay, fine. So the statement is saying there exists some optimal prefix code for C. So let's see how do we prove that. So let's say that you have a tree T representing an arbitrary optimal prefix code. So take any arbitrary optimal prefix code where this condition that X and Y are having same depth and they differ in only the last bit might not be true. Then what we do, we modify T to a new tree T prime such that the characters X and Y with the lowest frequencies appears as sibling leaves of maximum depth in T prime. So if we do that, then X and Y will have the same length code word, only differing in the last bit. Okay. If that is the case, finally we will show that okay, we have constructed new tree, and then we will show that T prime, this new tree prime, will also be an optimal prefix code. So we can construct it. So we showed existence of an optimal prefix code T prime where X and Y are having same length code word differing in the last bit. Okay. So let's understand this. So let's say A and B be the two characters that are sibling leaves of maximum depth in T. So I look at my tree T. What is T? T is nothing but some arbitrary optimal prefix code tree. Okay, it's the representation of some arbitrary optimal prefix code. Within that, pick up because remember, an optimal prefix code will be a full binary tree all the time. Okay, so if it is a full binary tree, there will be two sibling leaves somewhere with the maximum depth. Let's call them A and B. Okay, and let's say without loss of generality that frequency of A is less than equal to frequency of B, and of course frequency of X is less than equal to frequency of Y. Okay, what is X and what is Y? X is the least frequent character in C, Y is the second least frequent character in C. Since characters X and Y are with the lowest frequencies, you can immediately say that okay, since X is the least frequent one, definitely X is going to be less than A frequency. It is definitely less than B frequency also, because frequency of A is less than frequency of B. Y is the second least frequent one, so frequency of Y is definitely less than frequency of B. Okay, right? This comes from the fact that X and Y are with the lowest frequencies. So now notice that frequency of X cannot be equal to frequency of B, because if frequency of X is equal to frequency of B, then you are saying that Y frequency is less than equal to X frequency, which means X also you have said frequency of x is less than equal to y frequency, which means that frequency of x is equal to frequency of y, which is equal to frequency of a, which is equal to frequency of b. So that's the redundant case where I have to do nothing, because these all frequencies are same. Frequency of a and b are same, they are siblings, so they are having, x and y are the least frequent or the lowest frequent characters, so a and b are such two and they are siblings, okay, at the maximum depth, and they differ by one character, okay. So their code word lengths are same and they differ only in their last character. So I have nothing to do if x frequency is equal to b frequency. So our assumption here is that frequency of x is not equal to frequency of b, okay. So now let's say I got this tree T. T is what is T? Just recall, T is binary, tree representation of some arbitrary optimal code, okay, prefix code. Within that tree, A and B are the characters with the maximum depth. X is somewhere in this tree, so let's say X is there, okay. It is going to be a leaf somewhere in the tree. A is this, and then what we do is we swap between this X and A, okay, and we get a new tree T prime. Fine. So we have swapped between A and X in T, and we got a new tree T prime. Fine. Then in this T prime, what we do? We see that, okay, we swap again between B and Y, and we get a new tree T prime, T double prime. Notice that now what happens in T double prime, X and Y are siblings. That means their code words are of equal length, differing only in the last bit, okay. Only thing we will require to prove is that T double prime is is also an optimal prefix code. Then only we are done. So first thing you notice that what is BT minus BT prime? What is BT prime? BT prime is when you exchanged between this A and X, okay, the first step. So where you exchanged between this in T, you exchange the node X and A, okay. What is A? A is the character with the maximum depth. So what is the cost? BT minus BT prime, which is nothing but, if you break it up, it is nothing but this quantity, right? Frequencies of the character C in C times what is the depth of C in T. Here it is, what is the depth of it in T prime, which is equal to nothing but, if I notice, all the characters in T and T prime are intact. Only thing which has changed is between A and X there is a flip, okay. So all of them, all those frequencies will cancel out. What will remain is X dot frequency dtx plus A dot frequency dta minus X dot frequency times dt prime x minus A dot frequency times dt prime A, okay. So that will remain. These two terms are coming from here. These two terms are coming from here. The other terms of these two summations are cancelled out because they have not changed their positions, okay. So from T to T prime, only thing we did is we flipped X and A, okay. So now if we look into that, okay, this we simplify as X dot frequency dtx plus A dot frequency dta minus X dot frequency dt prime x. Now we replaced, what is dt prime x? What is, it's nothing but the depth of x in T prime. So just go back and see what is the depth of x in t prime. It is the same depth of a in t, right? So dt prime x is equal to dta, right? Okay. Also, what is dt prime a? It is nothing but dt x. Fine. Okay. Depth of x in t prime is 1, 2, 3. Depth of a in t is 1, 2, 3. Okay. Fine. So that holds true. Depth of a in t prime is nothing but 1. Depth of x in t is nothing but 1. So that also holds true. Okay. So essentially what we are saying here, that we replace these two quantities dt prime x and dt prime a by dta dtx. If you simplify that, that nicely comes out to be a frequency minus x frequency times dta minus dtx, which will be equal to greater than equal to 0. Why? Why this is greater than 0? Remember, frequency of x is what? It is the lowest frequent character. So definitely it is lower than a. Frequency of x is lower than a. So this quantity is positive or greater than equal to 0. What about this one? Depth of a in t minus depth of x in t. Recall, depth of a in t, what was a? Is the maximum depth element or character in tree t. So definitely dta is greater than dtx. So that is also greater than equal to 0. If you multiply two positive quantities, it is greater than equal to 0. Fine. Okay. So thus bt is definitely going to be greater than equal to bt prime. Okay. So I just flipped a and x, created a new tree t prime, where the cost of t prime is better than the cost of t. If I now do a flip between y and b by the same logic, I can show that my new tree t double prime, which I get from flipping y and b in t prime, I will get bt prime is greater than equal to bt double prime. So together I get bt is greater than equal to bt prime is greater than equal to bt double prime. But we know that t is my optimal tree. We know that this guy is optimal, which means bt double prime must be having cost more than bt, because bt is the optimal. So using these two facts, I have that bt must be equal to bt double prime. That has to happen, which means that t double prime is an optimal tree, and it is having the property that x and y are having same length code word, differing only in the last bit. Okay, so we have proved the greedy choice property, that the way we are choosing the least two frequent ones and making them as siblings and creating a new node whose frequency is sum of the frequencies of these two, that greedy choice property is perfectly fine, because you will always find an optimal solution in which this greedy choice is an element of your optimal solution. So it always holds. Okay, so it's perfectly safe to make that choice. So we have showed that. The only thing now we need to show is the optimal substructure property. Okay, so how do we show the optimal substructure property? Let's see. So let C be an alphabet in which each character C, small c, belonging to capital C, has frequency C, is just writing the complete sentence. Let X and Y be two characters in C having the lowest frequencies. And let C prime be the alphabet C with the x and y removed and a new character z added. Okay, so now we are showing you an optimal substructure. What we are saying is that, okay, you have your alphabet C, from that x and y are the two lowest frequent one, remove them and put a new character z, such that the frequency of z is nothing but x frequency plus y frequency. Okay, then we are claiming that let T prime be any tree representing an optimal prefix code for the alphabet C prime. So we got this new alphabet set C prime, and we are saying that, okay, what is the optimal code for this alphabet C prime? Let's call that as T prime. Then we will get the tree T obtained from T prime by replacing the leaf node for Z with an internal node having x and y as children, represents an optimal prefix code for the alphabet C. Okay, so if I have this T prime, then I can get my T by simply replacing the leaf node for Z with an internal node having x and y as children, representing an optimal prefix code for alphabet C. So I have an optimal substructure property that, okay, whatever is my greedy choice, I take that out. Look into the remaining sub problem. I solve that remaining sub problem, and then if I plug it in, I solve my entire original problem. Okay, so I have an optimal substructure property. Okay, so that's what it is saying. So let's look into the proof of this fact. So let's express the cost of the tree T which we are building in terms of the cost of the tree T prime. So now for each character C in C minus xy, which is nothing but C prime, we have dtc is equal to dt prime C, right? Okay, so if I look at T, how T is built, we started with T prime and just added wherever Z comes these two nodes x, y as children. Okay, so for every other character apart from x and y, the depth of that character in T is same as it is in dt prime, as in T prime. Okay, so we are not going to change anything there, and hence if I look into C times frequency times dtc is going to remain as C times frequency is the frequency of C times dt prime C. That is the depth of C in dt prime, because the depth in these two trees for the character C is not changing. So only concern is x and y. What is the depth of x in T? It's nothing but depth of Z in T prime plus 1, because in T prime you started with root and somewhere in your tree you had this character Z, and what you did, you just added x and y to it, okay, to get T. Okay, fine. So what it is saying is, okay, what is dtx in this tree T where I just added x and y? What is the depth of x? It is nothing but depth of Z in T prime plus 1. Same it is for dty. So now I can say that, okay, x times frequency of dtx plus y times frequency of dty. That means, if I look at T, only thing which I have added is x and y, two more characters. So what is the cost, incremented cost of the tree? Whatever was the cost of other characters plus x times frequency depth of tx plus y times frequency times, or frequency of y times depth of y in T, which is nothing but x frequency plus y frequency. Depth of tx plus and depth of ty both are dtz plus 1. Okay, dt prime z plus 1. Depth of z in T prime plus 1. So, and what is this x frequency plus y frequency? It is nothing but the frequency of z. Okay, so I can write this as z frequency times depth of z in t prime plus 1. Okay, or I can say this is frequency of z times depth of t prime in z, depth of z in t prime plus z frequency or frequency of z, which is nothing equal to frequency, nothing but equal to frequency of x plus frequency of y. So now immediately it comes out that what is the cost of bt, this new tree which you created, cost of bt prime, because everything else remains same, only thing which I added is these two. So it is cost of z plus x plus y, so I got these two terms. Okay, x frequency plus y frequency, because only thing which I added is this frequency of x times dtx plus frequency of y times dty, which turns out to be nothing but frequency of z in dt prime z plus x frequency plus y frequency. So this is nothing but the cost of t prime, because for rest of the nodes it remains same in t, plus x frequency plus y frequency. Okay, so essentially it means that bt prime is nothing but cost of bt prime, t prime is nothing but cost of t minus x frequency minus y frequency. Okay, so now we assume, let's say that, so once we have done that, let's say that this tree t does not represent an optimal prefix code for C, because if it represents, we are done. Okay, so for the sake of contradiction, we will say that let's assume t does not represent an optimal prefix code for C after doing this replacement. Then if that's the case, there must exist another tree t double prime such that the cost of t double prime is less than, strictly less than cost of t. Okay, so we started with t prime, from there we got t by replacement of this z with two children x and y. Okay, and then we are saying, okay, what do? Claim is that, okay, this t is also optimal, because if it is not, then I must be having another tree t double prime whose cost is going to be strictly less than the cost of t. Okay, but now we have already proved in the previous lemma that this optimal prefix code will have this x and y. What are x and y? X and y are the two lowest frequent characters, okay, as siblings. So let's say I form another tree t triple prime with a tree where x and y is replaced by their common parent z with frequency this. Okay, so I will have, some tree with this property. Let t triple prime be the tree where x and y, so you are taking in t double prime, you have x and y as siblings. It is the optimal tree, okay, and its cost is less than cost of t. So what it is saying is that, okay, since in t prime x and y are siblings, I replace that y by another common parent node z with frequency x frequency plus y frequency, and let's call that tree as t triple prime. Then by the same logic, you can show that cost of bt triple prime is nothing but cost of bt double prime minus x frequency minus y frequency, comes from the previous fact, okay, which we just showed, which is, now we know that, okay, bt double prime is less than bt, which means bt double prime minus x frequency minus y frequency must be less than bt minus x frequency minus y frequency, which in turn means that bt triple prime is less than bt prime. Okay, but this is a contradiction, because we said in the very beginning that t prime represents an optimal code for C prime, right? We said in the very beginning that we replaced this, t prime was the optimal prefix code, but what we produced is a new tree T triple prime with a lower cost, which contradicts the fact that T prime represents an optimal prefix code for C prime. So I must then, my assumption that T does not represent an optimal prefix code for C doesn't hold true anymore. Hence, T is the optimal prefix code for C, and hence we have proved the optimal substructure property. Okay, so I hope it is clear that how we are proving using two facts, the greedy choice property and the optimal substructure property, that this Huffman code algorithm always gives you an optimal prefix code. Okay, so thank you very much, and with this we finish off our discussion on greedy algorithm.